roots of complex numbers. When I write down 2 to the third, I mean 2 times 2 times 2, which of course is 8. We can say 8 is the third power of 2. When I write this, the cube root of 8, I mean tell me what number I would have to multiply 3 of in order to obtain 8. Well, of course, that would be 2. 2 times 2 times 2 is 8. We say 2 is a cube root of 8. In the last video, we looked at this complex number. We raised it to the 10th power and obtained 1024i. Well, that means if I were to say, find me a 10th root of 1024i, the answer would be root 2 plus I root 2. The question is, how in the world would we find that if we didn't already know it? That's what we're going to explore here. Let me remind you again from the last video. 1024i, that was the standard form answer. The trig form answer had been 1024 cis 90 degrees. Now let's remember where each of those numbers came from. The 1024, that came from 2 to the 10th power, and the 90 degrees, that was a simplification process. Originally we had 450 degrees, but we decided we had an extra 360 in there and we took it out. Okay, so where did those two pieces come from? Well, here was the original trig form problem. Obviously we got 2 to the 10th because originally our modulus was 2 and we were raising that to the 10th power. We got the 450 because the original argument had been 45 and we multiplied that by 10. Now, what we're trying to figure out is this. If I start here, how would I go backwards to obtain this? In other words, how do I go backwards? Well, let's start with the modulus. When I went forward, I had the 2, I raised it to the 10th power, and I got 1024. If you want to reverse that process, you would just have to take the 10th root. In other words, in general, you're going to be finding the nth root of r. 10th root of 1024 takes me back to the 2. Okay, that's pretty straightforward. What about the modulus? Well, my original modulus was 45, and I multiplied it by 10, which was the n, to obtain the 450. So obviously, to put it back to 45, I'm going to have to divide that argument, that theta, by n. 450 divided by 10 takes me back to the 45. However, because of that simplification step, I may need to add back in multiples of 360 degrees or 2 pi first. Well, that leads me to what's called de Moivre's theorem for roots. If you have a complex number written in trig form, z equals r cis theta, and you would like to find an nth root of that number, you can use this formula. We'll use w to represent our root. You're going to be taking the nth root of r, just as we said here, and then for the argument, you're going to be taking theta, you're going to be dividing it by the n, just as we said, but you may first have to add in multiples of 2 pi, working in terms of radians here. K standing for an integer times 2 pi, multiples of 2 pi. Now, take a look at this note at the bottom because this is very important. It turns out every number has exactly n nth roots, meaning exactly 2 square roots, 3 cube roots, 4 fourth roots, etc. And you can find all of them using this same formula by simply putting in different values for k. Remember, the k was that multiples number. So start with k as 0. If you fill in k as 0 right here, you won't even be having any multiple of 2 pi. That would be the simple case where you just take your angle and you divide it by n. Then you put in k as 1. That would be adding 1 multiple of 2 pi. And then k as 2, 2 multiples of 2 pi. Every time you add in another multiple of 2 pi, you'll find another one of the roots. Stop when you get to n minus 1 and you will have found them all. Obviously, if I was working in degrees, this formula would say plus 360 degrees times k. Let's take a look at an example problem. Okay, so we want to find all the square roots of this complex number, 9 cis pi over 3. First off, how many answers are we going to get? Well, remember, every number has n nth roots. So there are 2 square roots. Our n is 2 in this problem. I will have 2 answers, and I can find them both using this formula by plugging in the first 2 values for k. I know I'm going to be stopping at k equals 1 because I always stop at n take away 1. My n is 2. 2 take away 1 is 1. My first root, which I'll call w sub 0 because I'm plugging in the value of 0 for k, well, I'm supposed to take the nth root of the r. In this case, we're doing square roots, so the square root of 9, and then cis, and here I simply get my theta, pi over 3. I'm not adding anything to it because my k value right now is 0, and I'm dividing by my n, which is 2. Let's simplify. Square root of 9 is 3. Pi over 3 divided by 2. Dividing by 2 is like timesing by 1/2. So pi over 3 times 1/2 would be pi over 6. There is one of the square roots of the original number. The other one, which I'll call w sub 1, is found by going back to that same formula. Notice nothing changes at the front part. But in the argument part, now, in addition to the pi over 3, I add in 1 multiple of 2 pi. K is 1, and still dividing here by 2. Let's see, we need to do some scratch work here. So pi over 3 plus 2 pi, if I call that 6 pi over 3, to get a common denominator, that gives me 7 pi over 3. And then dividing by 2 is like timesing by 1/2. So it looks like I'll end up with 7 pi over 6. 3 cis 7 pi over 6. The original number has 2 square roots, and here they are, 3 cis pi over 6 and 3 cis 7 pi over 6. What if you wanted to check yourself? Well, all you would have to do is square the numbers and make sure you get back to the original. I mean, after all, that's what a square root is. We're claiming that if you multiply 3 cis pi over 6 by itself, you'll get back to 9 cis pi over 3. Well, this is just the regular version of de Moivre's theorem. Take the r, raise it to the power, take the argument, multiply it by that number. And of course, if you do this, you very quickly get 9 cis pi over 3. Well, how could that same thing work on the other one as well? Take a look. 3 cis 7 pi over 6. Let's say I wanted to square that. Well, square the 3. Multiply the 7 pi over 6 times 2. That gives me 9 cis 7 pi over 3. But 7 pi over 3 is too large. It's bigger than 2 pi. I would subtract out 2 pi, in other words 6 pi over 3, and when I do that, I land right back there at 9 cis pi over 3. And so our answers are correct. One last comment here, and this will become important. What if I was to draw the 2 answers we just got? The first one, 3 cis pi over 6, that means rotate an angle of pi over 6, that's about 30 degrees, and go out a distance of 3 units. So something like that. That dot represents the first answer. The second answer, 3 cis 7 pi over 6. 7 pi over 6 is 210 degrees. That's 30 degrees past 180, which means it's exactly on the other side here. It's very symmetrical and spaced out. Here is the W1 answer. In fact, if I formed the circle centered at 0, 0, containing those 2 points, my 2 answers would be equally spaced out along that circle. We'll keep that in mind as we move to the next example. Okay, here's our next example. Find all the cube roots of 8. Now you may think, what a silly problem. I already know what the cube root of 8 is. It's 2. 2 times 2 times 2 is 8. Well, that is true. That is one of the cube roots of 8. But there must be 3 in all, because we know that every single number has n nth roots. There are 3 answers here. This de Moivre's theorem for roots can help us find all 3. Now, maybe you're thinking, but 8 isn't even a complex number. It's just a real number. Well, the real numbers are a subset of the complex numbers. This is just the complex number 8 plus 0i. If I was to mark it down, it would land right here in the complex plane, which means the trig form of the number 8, well, clearly the r, this distance, would be 8. And the angle, I can tell, is 0 degrees or 0 radians, 8 cis 0. Now that I have that, I can apply de Moivre's theorem for roots. The first one would be w sub 0. According to the formula, I take the nth root, which in this case would be the cube root of the 8, and then cis, and remember the first time there is no multiple of 2 pi. It would just be the angle, which is 0, divided by the 3. Well, this works out to be 2 cis 0. Cube root of 8 is 2. 0 divided by 3 is 0. That would be the trig form version of the answer. But let's convert that to standard form. 2 cis 0, I could mark it on this same picture right here. That would be right here. Rotate 0 radians and go out a distance of 2. Well, that's just the real number 2. It's 2 plus 0i, which is 2. There's that 2 we knew we were going to get. We knew that the cube root of 8 is equal to 2. But there's a couple other answers as well. W1 will give us the next one. Once again, cube root of 8. And then in the argument part, it's going to be the 0 plus the first multiple of 2 pi, and then divided by 3. This simplifies to be 2 cis 2 pi over 3. Let's write that out the long way and switch to standard form. Let's see, I need to know what cosine 2 pi over 3 is and sine 2 pi over 3. 2 pi over 3 is 120 degrees. My reference angle would be 60. So I've just got a 30, 60, 90 triangle. The 1 there would be negative. The cosine value looks to be negative 1/2. And the sine value is square root of 3 over 2. When I multiply through by that 2 at the front, all the 2's will cancel. And so I'll end up with negative 1 plus I root 3. This is another cube root of 8. Now you can see why we didn't know about this one at the beginning. We're not saying that every number has 3 real cube roots. We're saying that every number has 3 complex cube roots. Now in this case, one of those 3 complex roots happened to be real. This one is simply complex, and I'm sure the third one will be complex as well. Let's go ahead and find it. The third one will be very similar. It's cube root of 8. Now I'm adding 2 multiples of 2 pi. My k is 2 now. So that top part is going to end up being 4 pi. This will end up being 2 cis 4 pi over 3. Let's convert that into standard form. Let's see, I'll need a new picture, although it's really very much the same. 4 pi over 3 is just the symmetrical triangle over here in the third quadrant. So the only thing that changes is the square root of 3 is now negative instead of positive, which means my values will be the same, just both negative. So negative 1/2 and negative square root of 3 over 2. Once again, the 2's cancel, and so I end up here with negative 1 minus I root 3. That is the third and final cube root of 8. Okay, lastly, let's draw a picture of these 3 answers in the complex plane. It's easiest to do that using the 3 trig forms. So I had 2 cis 0, that's rotate 0 and go out 2 spaces, so that would be right here. There's the first one. The next one, 2 cis 2 pi over 3. 2 pi over 3 was 120. So go to 120 degrees and then go out about 2 spaces there. And then 4 pi over 3 is 240. So that's going to be about here, going out 2 spaces. Well, do you see that the same thing happened as the other time? If I connect the 3 points with a circle, I've ended up with 3 answers that are equally spaced around that circle. In the last problem, I had 2 answers. They are 180 degrees apart. 360 divided by 2 is 180. In this problem, I had 3 answers. They are all 120 degrees apart. 360 divided by 3 is 120. We can use this equally spaced fact to speed up our work in these problems. And let me show you that in one final example. So I want to find all the 6th roots of the number I, the complex number I. Okay, the first thing I need to do is I need to figure out the trig form of I. If I wrote it in standard form, it would be 0 plus 1i. If I graph that in the complex plane, I wouldn't go left or right. I would just go up 1 space here. Here's 0 plus 1i. Well, the picture tells me what I need to know. Clearly, the trig form of that number, the r would be 1, this distance right here. And I can see that the angle would be 90 degrees. Why don't I work in degrees this time? So 1 cis 90 degrees. Okay, once I have my trig form, I can start using the formula to find my roots. I know there's going to be 6 in all, so I'm going to have to use k as 0, 1, 2, 3, all the way down to k equals 5, since 6 minus 1 is 5. How do I do this? Well, first I take the 6th root of the r, the 1, and then for the angle, the first angle that I do, I don't add on any multiples. If I were going to add on multiples, I would have to change the 2 pi to 360 since we're working in degrees. But for this first one, I would just have the 90 degrees divided by my n, which is 6. And let's see, 6th root of 1 is just 1. And 90 divided by 6 is 15. I don't really even need the 1. It's not doing anything. And so my final answer for that first square root would be cis 15 degrees. That's my first of 6 different answers. Now, obviously, I could find W1 and W2 and W3 using the same formula, but I don't really need to go through all that work. We have learned that our roots are always equally spaced. Well, if you have 6 roots, all you have to do is take 360 divided by 6 to determine that all of your answers will be 60 degrees apart. It has to work out that way around that circle. So I don't really need the formula. All I have to do is add 60 degrees over and over and over. So I get 75, and then I get 135, and then I'd get 195, and another 60 would bring it to 255, and the final one is going to be 315. There are the 6 roots of that original number written in trig form. By the way, if you kept going and you went another 60 degrees, you'd be at 375. That's past one full rotation. If you take away a 360 from 375, you're just back at the 15. In other words, you'd just be finding the same ones again. We have found all 6. Once you understand this pattern, the problems become so easy to work out. Find the first one using the formula, and then for all the rest, the r is going to stay the same each time, and the angles simply change by that equally spaced amount. Write them all down, and you're finished. Thanks for watching all these trig videos.